Okay, perfect. Is that looking good?
Yeah, fine.
Okay, so a quick introduction. I think always the workshops are better when we have some time for unstructured discussion, and that's difficult with Zoom and the way that we're doing things these days. But in the workshop, we have put some time for discussion. Today, later on at 1 p.m., Matt Kohler will lead the framing discussion session. And then tomorrow at noon, Bill Rand will lead these concluding discussions. Also, we have 3 breaks today, and we encourage everybody that wants to, have some unstructured discussion on the Zoom channel to please do so. And so today I'm going to start, jumpstart a little bit the discussion and hopefully frame a little bit before, for the rest of the workshop. So one of the things that I think are important with the emerging field like inverse generative social science is agreeing on things like definitions, methodology, what are the challenges, what are the opportunities of this emerging field. And I will talk a little bit about that, summarizing what we have discussed so far. And also, I will provide a glance of some research we've been doing with some collaborators in the room about a first approximation of IGSS on something we call evolutionary model discovery. So the forward question is, recapping a little bit what Josh said yesterday. The main question for me is giving a set of micro rules or generators. What is the resulting macro phenomena? And if we do this computationally, that's an ABM. So giving a set of micro rules, compute the resulting macro phenomena, and deciding or designing ABMs is to, in some way, handcraft the right set of rules that generate the macro phenomena of interest. And this sometimes involves trial and error, intuition, domain knowledge, etc. In the mathematical world, an analogy will be game theory, because in that we have a given set of rules and we calculate the possible outcomes of a game. So if we look at the backward direction, the main question here change is basically given a macro phenomenon of interest, what are all the possible set of micro rules that can generate it? And in what we call EMD, we look at the given macro phenomenon of interest to compute the class of all sets of micro rules that can generate it. And then designing an EMD is to handcraft again, at a different level, the right representation that allows for a meaningful, a feasible exploration of the search space of plausible generations for a given macro phenomena. And that, again, on a different level, but also involves trial and error, intuition, domain knowledge, etc. And the analogous in economics will be mechanism design theory, which is sometimes referred as reverse game theory, which is giving a game's desired outcome to calculate the mechanisms or the rules of the game that will allow for that outcome to happen. So when I look at IGSS, I see it as a system that produces 2 outputs, in my view, and this is something for, of course, for all of us to debate. But the output number 1 for my IGSS systems will be the class of generators. So either ideally an exhaustive and complete enumeration of all the possible generators for a given macro phenomena. In practice, probably a limited, a good enough set of generators. Each one of these generators, of course, defines a valid model for the phenomenon of interest. And another output of IGSS, in my view, is the characterization of that set. So once we have all the set of potential generators, then we need to figure what the set is telling us about the modeling or the phenomena we're trying to model. So are all generators different? So they are unique. Are they all identical? So there is only one possible generator set or generator on the set. Can they be grouped or classified in some sort of criteria of interest? Do they have elements in common? They have common rules. So there is a rule or a factor that is common across all the possible generators for a given phenomena. And also, can the models that are generated could be classified or grouped in some sort of way with some metric of interest? So, and that leads me to what I think, in my view, and this is a discussion point, on what is important on iGSS. So in my view, it gives us a more robust story to tell when we're modeling phenomena, because we don't have a single model, but a systematic exploration of classes of models that can possibly generate a phenomena. Also allow us to answer questions of the like as under which circumstances a phenomena emerges, if the phenomena is stable. For instance, if democracy is stable, what are the possible scenarios in which we can model that outcome. Also, what Scott was saying yesterday about if you change parameters, it gives different results. So I think with this method, we try to put to rest those kind of criticisms where we can have a robust model across all sets of possible parameters across many different models that generate the same phenomena. Another thing that I think in my case personally, I found attractive and interesting on iGSS is the case of causal inferences, because once we have a set of generators, what we can say about that set is stronger than what we can say about a single model. For instance, if all generators of a given phenomena include a rule X, that implies that X is a necessary condition for generating or modeling that phenomena. So, and again, this is a discussion point, so many other ideas could go here, and hopefully we discuss this in the later sessions. So just a quick slide on opportunities. Again, this is just a prime to start discussion. Some of the things that I have heard is, well, one of the opportunities for iGSS is the inexpensive computing power, the clever AI ML algorithms that can help us doing massive searches on things like the generator search space. We also have massive amount of data, behavioral data, and that Bill make a reference to small and large data yesterday. We have large amount of libraries of models, mathematical models, and Rob Axtell talk about agentization. So we can leverage these existing models to dock into new classes of generators in iGSS. Another, I think, opportunity for the community is the current emphasis on explainability in artificial intelligence. And as we all know, this type of iGSS is a complete glass box in comparison with black and white boxes approaches. Being completely ontologically correspondent, and every decision could be explained by a previous decision in the model. So also, I think, in my view, another opportunities is what Scott Page was talking about yesterday, which is stability of democracies, polarization, algorithmic decision-making, and all these forces that are at play on this time and age that I think are right for iGSS type of studies. And of course, many others, and hopefully we have many opportunities to discuss this throughout the rest of the workshop. In terms of challenges, I think Tim put it yesterday as a bounding the search space, and I think that's a very important view. We cannot speak about studying an infinite set of infinites. So in some way, we have to find finite search spaces that are meaningful. Josh, in terms of challenges, yesterday he mentioned about a better mousetrap, or show me the mice. So in some way, iGSS need to produce better models, right? Bill mentioned data standards, model representation standards. Also, challenges are formalism and methods of an emerging community, and characterization, as I mentioned, of generator class, and many others. So now, in the next 10 minutes or less, I'm going to discuss a little bit of a simplification that we make in order to implement these ideas of iGSS. So evolutionary model discovery was introduced by Chatika in his dissertation. And basically we say, okay, generator space is infinite. So let's make it finite. And to make it finite, we have a finite set of factors that we call primitives, a finite set of operators that recombine these primitives into what we call a factor tree of finite depth, and that bounds the entire search space. And we also bound the search space in another way, which is we don't explore complete models for a given phenomena. We just explore established models, and we change only one subsection of an established model. For instance, in the Anasazi model, we focus on the farm plot selection mechanism, and in the Schelling model, we only look at the relocation mechanism. So we take an established model, so we have a place to start, and then we do an IGSS type of study on only one subsection of that model. And that also helped to bound the search space. For the generator search algorithm, we use genetic programming, given that we're working with trees in the factor trees. And as a generator class characterization, we use random forest regressor and factor importance analysis just to have an idea of what are the important factors in the class of all generators. So for just a very brief glance on what we did with the Anasazi, as I mentioned, the submodel analyzed there is factor affecting farm plot selection. And these are the variants or the hypotheses for factors that we introduce. We introduced some of them related to social connectivity. Some of them, they are related to the quality of the land, like comparison of quality, comparison of dryness, comparison of yield, water availability, distance, homophily by age, homophily by agricultural productivity, social presence, migration, and others. So these are different hypotheses that could explain the reasoning of the Anasazi or the motivation of the Anasazi, the causes that led them to change and move to a different or select a different plot, right, when their plot is exhausted. So this is a very known model, of course, by Josh and Rob Axtell. So when we're talking about IGSS class of generators, here's a quick list of some of the generators we found that have high fitness. So as you see, they are widely different. However, if we study the class of generators, we can see that the top factor is quality, and that's in contrast with the original factor, which is just the distance, right? The close distance is in the original model. In our IGSS study, we found that this is the order of factors in order of importance. So what we can say here is something a little bit, I think, bigger than if we have a single model. What we can say is in all the models that potentially can generate the Anasazi outcome of population distributions over time, the quality of plot is the most important factor across all the models. And in terms of robustness, the top 3 models are generated with this evolutionary model discovery. The top one is the original one, and we ran them from a randomized set of initial parameters. So you see they are robust in initial parameters, and also you can see that what we can tell about these models in the top right is that the ancestral pueblo peripheral farming locations with higher soil quality, higher social presence, and further away from areas where farm plots failed previously. And again, that's what we show on the top models, and in different variations, these factors are present and they're important. And again, in contrasting with the model at the bottom, which is just the minimum distance to the next farm plot. So we did something similar with segregation and Schelling. The submodel analyzed there was the factors affecting residential location utility. So the reasoning behind moving from one location to another. And this work is still underway, but is in collaboration with Chatik again, Eres Hatzna, Josh, and myself. And these are the list of factors to the right. The fraction of racial similarity, mean neighborhood tolerance, diversity, neighborhood isolation, length of residence, mean satisfaction, diversity satisfaction, etc. So, and tendency to move, which is that it turns out to be very important if we look at the results. So this is just the class of generators, again, the set of top performing alternative models or generators that create these models, and the different factors that they combine. And when we do the factor analysis, we see that move is the top factor, even more than in the original model, which was race. And by move, we mean the resistance, because if we see on the next slide here, you see move in negative as a negative factor. So what we can look at here in this is that, or the results is that in order to generate these mixed patterns for which we use the Hamna-Benson model, are caused by resistance to moving from the current location, preference for less crowded neighborhoods, and preference for higher Russian similarity. So which come on third place, as in contrast with the original, of course, model, which was the only factor considered. And again, here we have a runs of this, the subset of models with randomized initialized parameters. So that shows the robustness across the solutions. So just to summarize, in my introduction, I give you forward and backward modeling, at least how I interpret them. What are the advantages of use IGSS in a modeling study? Some of the challenges that derive from the computational complexity of conducting this type of studies, and also to the need for define some good example problems on which this method shows that this is better, as well as a standard methodology, characterizations, etc. Some of the opportunities, including AI, of course, helping in many ways to do the search and to do the analysis of the models, agentization, current events. And I have shown you a first approximation in evolutionary model discovery. And we have some publications on that. And I see today we have Chatika's talk at 3 talking about polarization, and also Mariah's talk at 3:30 talking about radar models. And then tomorrow we have Lux's talk on EMD talking about irrigation models. And just to mention, the EMD toolkit is available in the link below. Okay. That's all I have, and we have 5 minutes for some discussion on this before we start with our talks of the day. Let me check.
How do you do that?
If
nobody else is going to step forward.
We have.
Hey, Josh.
hey, no, that's okay. I was just going to say that was an absolute superb talk. Thank you very much, and I hope you're posting the slides.
Thank you, Josh.
Really wonderful.
Absolutely.
Absolutely great.
We have some hands up. Tim and Ann.
Yeah, Tim was first.
Okay.
Okay. So let's see. So yeah, I guess in your list of kind of well, how do I? It's early in the morning. It's already here in the West Coast, so I'm not thinking as clearly as I should be. But when it comes to generating these giant spaces of generators is a somewhat alarming prospect to me. I think it's important, but it's also alarming. And there's the searching an infinite space blindly is, of course, a completely losing proposition. Usually you're starting somewhere near the middle with a null hypothesis and kind of working your way out algorithmically. You never really get out to infinitely complicated Rube Goldberg explanations just because you don't have enough computing power and time. But the bounding the space, which thanks for the shout out there. Yeah, I think that's important. But maybe there's another thing there, that what we're seeking, I think, with this generative enterprise is still explanation. It's still causal explanation. It's still meaningful human stories that we can tell about why things work the way they do. Though it is notable that the hand-rolled algorithms often aren't very good compared to what a machine can come up with. But there's this interesting dance between what the machine can come up with by whatever clever methods we come up with, and the need for human understanding, and I think is ultimately the point of the scientific enterprise. And figuring out how to get from one to the other, I think is still really interesting. And we potentially end up lopping off pieces of the space, but still ending up with non-explanatory predictive explanations. Or anyway, you know what I'm trying to say.
Yeah, good point. I think it's not only bounding the search space, right? Because then you can have a searchable a space that is hard to interpret or meaningless or too convoluted for being used to anybody, right? So I think it's not only bounding search space, it's what type of knowledge representation you use in order for the recombinations on the exploration to be meaningful for in an explanatory point of view, right? And that's a big, I think I would argue, a big open question on the community. I mean, what is the universal modeling language that is meaningful, that could recombine theories from social science, psychology, etc., as well as data-driven nuggets of wisdom? How that can be all incorporated into some sort of lingua franca, where you have explanatory power and search ability. I think that's a big challenge.
I just want to add something there. I think that's a great point. And as Ivan pointed out earlier, we start with evolutionary model discovery. We start with agent-based models that already exist, and then we look at a particular point in the agent decision-making process, and we investigate how that particular decision would have been made with a limited set of hypothesized factors. So we're at that point, we're utilizing a lot of existing domain expertise, which went into constructing the whole agent-based model, constructing how and when the edges are scheduled, the environment they exist in, the interaction pathways, and then we're looking at a particular point in their decision-making process with a set of hypothesized factors that we draw again from existing literature. And then we experiment with how they combine. Of course, how they combine, the number of combinations theoretically can produce a infinitely large search space, but then we limit that again with max depth in the genetic program. So there's a lot of scoping down. Yeah.
That seems like a very powerful approach. Yeah.
Can I tiny footnote? Thank you, Shadiko.
Of course.
The other I think wonderful move is the intersection of the rules. You know, to find the germ that is common to a cloud of generators. I think that's also a very important move that might help say, look, there's this cloud or neighborhood or set or something of these generators, but here's an element that lots of them have in common. Maybe, Tim, that would help isolate the really, the most important explanatory factors.
I'm glad that some generation of discussion also was produced. So I think we'll have to rely on the breaks, and then at 1 we have Matt for more discussion, and tomorrow Bill at noon for more discussion. So without further ado, I think we should start our sessions today, and we have Aaron Branson. Aaron, floor is yours.